Today I'm going to bring you back into the lab and show you another type of reaction. We're actually going to do 3 today. The first one of which is a single replacement reaction. Let me put a little graphic up here for you to see. And this reaction is going to take zinc and hydrochloric acid and transform them into zinc chloride and hydrogen gas. What we mean by single replacement is the zinc's going to come in, knock the H off the HCl, combine with the Cl, and then when the H is knocked away, it eventually combines and makes H2 gas. And you'll see all the little subscripted phases that I have at the bottom. Zinc is solid, hydrochloric acid is aqueous, AQ, the zinc chloride will be aqueous, and then the hydrogen gas will be a gas. Okay, so let's give this a try. The acid I'm going to use is 6 molar hydrochloric acid, which is very strong. It's about half the strength of the way that we buy it, 6 molar HCl. The zinc is a metal, and I have a bottle here, and I've taken a piece out, which we'll use. So here's the piece of zinc. It looks like a little block, kind of gray. This is fairly stiff, but you could hit it with a hammer and start to reshape it. So I'll take a large test tube like I did yesterday and clamp that into the support stand. And under the test tube I have a little petri dish, so if anything overflows I'll be able to catch that. So here's our setup. I'll bring this up a little closer so you can see. Test tube with the clamp behind it. Now I'm going to put some of the 6 molar hydrochloric acid in. I'm going to need 10 milliliters, so using the graduate I'll pour that in. There's our 10 milliliters. This is strong, so I got to be careful with it. And then I'll put this down in the sink so I can later on rinse it out. I'm going to return my zinc. I'm going to return my hydrochloric acid to this bottle. I know I haven't contaminated it at all. And I'll clean this speaker out when I get a chance. Now let's take our piece of zinc. The zinc, being a metal, is pretty hard. So when I put the piece of zinc into the test tube, I'm going to slide it in so it hits the bottom of the test tube gently. And it's at the bottom, and it's starting to fizz. I'm going to cover over the top of the test tube with a cork. And the cork is going to be kept on loosely because I want to trap the gas. I measured my acid before, and the temperature of the acid was 24.8 degrees. We can say 25. I'll bring this up a little closer so you can see what's going on in the test tube. Got a lot of bubbling. Now, hydrogen gas is being given off. So I'm going to try to test that, and the way I can do that is to use a little barbecue lighter. I'll lift off the top of I'll lift the cork off the top of the test tube, and then I'll bring a flame over to it. And we got a little pop. Let a little bit more of the acid decompose the zinc. And we'll probably get a little bit more hydrogen. And let's give this a try. The bubbling is still going on. Another pop. So as long as I still have the bubbles coming off, I know I have zinc coming off. The next thing I want to do is to tell you and show you that the reaction down here in the test tube is changing temperature. We started at about 25 degrees Celsius. I'm going to check it with the thermometer right now. So this is a single replacement reaction where the zinc is coming in and kicking the hydrogen out of HCl, so that involves breaking of bonds. So we should have a temperature change. Let me read it. We are up to this is a thermometer that has both Celsius and Fahrenheit listed on it. And right now it's reading about 50-some degrees Celsius, so the temperature has increased. I can hold the test tube with my fingers, but it is warm. Now, let me cover over the test tube. Eventually what I'll do is I'll dilute the acid and recover the piece of zinc metal. Now, what I'm going to do is stop the video at this point and come and get another experiment ready for you, and then I'll be back. So here's what happened in that little break in between. I've taken all my glassware, I've rinsed it out, I've recaptured the solution with the zinc chloride in it, and it's kind of a grayish liquid. There's little pieces of zinc that have broken off there. I can eventually pour that down the sink, and then the piece of zinc itself, it's probably a tiny bit lighter, a little bit wet here. Let me dry it off. It's a little bit lighter, and some of it has dissolved away, but that's going to be hard for you to see. You can see there are some pits in it, but you'd have to leave the zinc in there for a long time for it to totally disappear. So it has dissolved a little bit. Now I'm going to stop the video again and get ready for the next phase of the experiment. We'll be doing a double replacement next. Now for our fourth type of reaction, the double replacement reaction, my chemicals are sitting here on the lab table. I'll tell you what they are in just a second. Then I'll be doing the reaction for you. I'm going to be moving that test tube that we just used over onto this tray so that I can do the same kind of reaction, same setup of reaction, but do it in the large test tube. So let me pause the video for just a second. So here are the reactants we're going to put together for the double replacement reaction. Put the graphic up here for you. It's going to take place between barium hydroxide and ammonium chloride. Ammonium chloride's on the left there, NH4Cl. It's a solid. The barium hydroxide, the AOH taken twice, is aqueous. And then eventually, when these things combine, we're going to get barium chloride, BaCl2, and ammonium hydroxide, NH4OH, both of which are aqueous. So a double replacement reaction. This is where the two sets of chemicals switch ions, like two partners in a dance. They meet another couple and they switch partners. So for our reaction here, let me show you the chemicals we're using. My ammonium chloride is the solid. We store it in this large bottle. And then the other substance is the barium hydroxide. That started out as a solid, and then I made it into a solution, and I've saturated it so there's a lot of barium hydroxide mixed in with the water. So my solution is pretty strong in barium hydroxide. When I poured that barium hydroxide into a beaker, it looks almost like water, although it's a little tiny bit cloudy towards the bottom. And you'll see there's a little film that's starting to form on the side of the beaker. Right now what's happening is the barium hydroxide is actually reacting with some of the carbon dioxide in the air, and it's forming that little cloudy film. Not going to hurt our reaction, but that's one of the little side effects that's here. So let me measure out what I need. I'm going to take 10 milliliters of the barium hydroxide solution, and we're going to register its temperature. And I have a temperature probe once again, and I have a little LabQuest here so that we can see what the temperature looks like. And this has been sitting in the room, so it's reading room temperature, 23.2 degrees Celsius. The next thing I'm going to do is pour this into our test tube. And then a little earlier, I measured out using one of our scales. I measured out the ammonium chloride. I put it in a pan. It's a white crystal. You might be able to see a little bit of it there. And I'm going to dump that into my test tube. Crystals drop in very nicely. Let me give the test tube a little swirl here to catch the stuff that's gotten on the side of the test tube. Some of the crystals are up against the glass on the side. Then I'm going to shake the test tube and get the two to react with one another. So there's my crystals at the bottom. Agitate them with the solution. The crystals are starting to dissolve. So you see less and less crystalline material at the bottom. And then we're going to test the temperature. A double replacement reaction is taking place, so the two compounds have switched partners. I'll just support that again. My temperature probe is in there. We started out at about 23 degrees Celsius. And now our temperature, let me see if I get that in position for you. Our temperature is down to 17.5 degrees Celsius. So the reaction here has really cooled down. And in fact, if I touch the test tube down here, it feels almost like an ice pack. It's cooled considerably. So in this double replacement reaction, it actually is sucked in heat from the surroundings. Okay, I'm going to stop the video again and I'll show you the final reaction. For the fifth and final type of reaction, we're going to do an experiment where I'm going to show you a combustion reaction. I've turned the lights out in the room here so that we can see the combustion better. I'm going to be doing a reaction that's similar to the combustion that you get when you're doing an experiment using the Bunsen burner. I'm going to be taking methane, CH4, in a gaseous state. We're going to be burning it in the presence of oxygen, also gaseous. The byproducts are going to be carbon dioxide, and that's gaseous, and water vapor. So typical combustion, most combustions do the same thing. You start with the fuel, you have an oxidizer, and your byproducts tend to be carbon dioxide and water. Now, to do the experiment, I've taken a can that used to hold peanuts. I put a hole in the metal base of it, and then up towards the other end, right near the opening, I have a little hole that I cut into the side of the can. So what I'm going to do is take a can, put it on a gas jet, add a little bit of gas to it. The gas is pushing air out of the can, and in a second or two I can smell the methane coming out into the room here. So about 20 seconds worth of gas. Let me turn that off. Now the gas is going to want to leave the can simply because the methane is a little bit lighter than the air in the can. And what I'll do is I'll light the top of the can here, actually the bottom of the can, and where the metal is, and we'll let it burn. I've turned the lights off so that you can see the combustion a little bit better. And typically what happens with a flame where you have unburned byproducts of the combustion, in other words, particles of carbon, because the methane isn't completely combusted to CO2, it'll make those little carbon particles glow, just like the candle does, and that produces that yellow color that we see. Within the room here, I have to be a little bit aware of where the air system is blowing air around, so I hope I picked a good spot, because I try not to have too much of the